Welcome back to the LangChain Masterclass. Up to this point in the series, we've explored how to work with LLMs, how to build prompts, how to structure outputs, and even how to enforce strict schemas for reliable data. But as your AI application grows more complex, a single prompt or a single model call is no longer enough. Real world AI workflows are rarely one shot. They involve multiple steps. One step generates something, another transforms it, another validates it, another analyzes it, and another uses the output to trigger a choice or an action. And unless these steps are connected, orchestrated, and executed in the right order, your AI system becomes unpredictable and impossible to maintain. And this is where chains enter the picture. Chains are the backbone of LangChain's workflow ecosystem. They allow you to combine multiple operations, model calls, transformations, utility functions, data processors into a single, reusable, and reliable pipeline. Chains help you go from a single prompt to a structured multi step AI workflow that behaves the same way every time you run it. In this episode, we're going to explore four essential types of chain that every LangChain developer must master. The four chains are: the first is simple chain, where a single input leads to a single output. The next is the sequential chain, where multiple steps run one after another like a pipeline. And the third is the conditional chain, where different branches execute based on rules or model output. And fourth is the parallel chain, where multiple tasks run side by side to save time and improve efficiency. Each of these chain solves a different class of problems, and by the end of this video, you'll know exactly which one to use and when. So why do we need chains? Let's look at real problem scenarios. Imagine you're building a resume analyzer. One step extracts the details, another step cleans them, another summarizes the candidate's background, another evaluates the experience level, and so on. If you rely on a single prompt for all of this, the output becomes messy, inconsistent, and impossible to control. A chain helps break this into clean, manageable steps. Or consider content creation system, where you first generate an outline, then expand each section, then refine the writing style, then correct grammar, and finally create a meta explanation. Doing this in one prompt leads to bloated outputs and hallucinations. A chain lets each step handle its own responsibility. Or imagine building an intelligent agent that needs to choose between multiple options like retrieving information, generating content, or calling an API. Without conditional chains, your agent has no structured way to choose paths. And finally, think about the use cases where generating multiple items at once saves time, like summarizing various sections of a document simultaneously. And that's where the parallel chains shine. So in this video, we're going to break down how chains work, how they enable step-by-step logic, and why they form the foundation for building advanced agents, tools using systems, and multi-stage AI pipelines. And by mastering chains, you'll unlock the next level of LangChain development. We will start with a simple chain. A simple chain is exactly what it sounds like: a single linear flow from input to output, where you provide an input, it passes through a prompt, the language model processes it, and finally, a parser cleans or formats the result, and then we get an output. There are no branches, no choices, no multiple steps, just one clean, straightforward pipeline. Think of simple chain like a conveyor belt, where the object moves from one station to the next without interruption. Basically, one prompt will lead to one model call, and that will lead to one output. Simple chains are perfect for tasks that need consistent single step transformations like generating text, extracting a short answer, rewriting or summarizing content, or producing quick structured text snippets. They keep your workflow clean, predictable, and easy to trace. Another major advantage of simple chain is composability. Each component, the prompt, the model, and the parser here is modular. You can easily swap out any one of them while keeping the chain intact. If you want a more detailed prompt, you can replace the prompt. You want a different parser, you can swap it. The chain still behaves the same way, just with a different internal logic. But the real power comes from how LangChain lets us build the chains visually and programmatically. Because each step is defined clearly, you get a transparent, debuggable workflow that you can inspect, visualize, and reuse across your applications. Now, let's connect this concept to the use case in our program. In the implementation that we're going to do, our simple chain will follow a classic 3-step flow. First, a prompt will ask the model to generate 3 facts about a user-provided topic. Then, a model call will process the prompt and generate the text. And then finally, a string parser will clean the output and give us a nice final answer. So these 3 components will be connected in a single linear chain. And when we invoke a chain with a topic, the chain will automatically run each step in order and return clean, ready to use text. And because it's a simple chain, the entire flow is easy to understand and perfectly suited for quick generation tasks like this. We even visualize the chain using its built-in graphic representation, which shows exactly how the data flows through the pipeline. Now, we'll move on to the implementation of our simple chain. Here, we'll first import the chatgrok class from LangChain _grok import chatgrok. Then from .env, we'll import load.env from LangChain _core .prompts. I'm going to import prompt template. Then from LangChain _core .output parsers, I'm going to import str output parser. Then I'll call the load_.env function, define my model. So my model will come from chatgrok class, and then I'll be using a llama model here as my LLM. Now I'm going to define my prompt, and then that will be defined using my prompt template. Template equals to generate 3 facts about a topic, and then I'll provide the topic as a placeholder here. Now, since we have a placeholder, we need to define our input variables. So my input variables will be the placeholder that I have here. So it will be topics. Now I will define my parser object using str output parser. Then I will define my chain here. So the chain will first generate a prompt. It will pass the model or the prompt to the model. Then the model output will be passed to the parser, and then the parser output will be generated. So if I need to invoke this chain, I can simply call chain dot invoke and then pass in the topic that I've represented here in the form of placeholder. So the topic can be aliens. And then finally, I can print out the result. So in the result, I should get a 3-point fact, basically 3 facts about aliens here, and then it should be in the string format. So now let me run this code. Chains on simple chain .py. Okay, so I have these 3 facts about aliens here. So this is the implementation of a simple chain. As you can see, It's a simple linear chain with a prompt, a model, and a parser. Now that we understand simple chains, let's move to the next level of workflow design, the sequential chain. A sequential chain is essentially a pipeline made of multiple simple chains connected one after another. Instead of transforming the input once, you break the task into several ordered steps where the output from one step becomes the input for the next. Think of it like an assembly line in the factory. Step 1 creates a rough shape, step 2 refines it, step 3 polishes it, and step 4 adds the finishing details. Each stage handles a very specific responsibility, and because the tasks are separated, the entire process becomes more reliable, interpretable, and reusable. Sequential chains are incredibly helpful when your workflow cannot be completed in one shot. For example, generating an outline, then turning each point into content, or extracting data, then cleaning it, then summarizing it, or generating a concept, then translating it, then rewriting it in a specific style, or doing multi-phase reasoning where each phase needs isolation. But with a sequential chain, you get a clear structure. Step by step reasoning, each performed intentionally without overloading the model with too much context at once. Another strength is how easy it becomes to debug. When something goes wrong, you know exactly which stage misbehaved. And because each step is its own mini chain, you can reuse, replace, or enhance individual stages without breaking the whole pipeline. So, in the example that we're going to do for sequential chains, we will follow the structured multi-step approach. We'll have a first chain that generates an explained piece of content based on the user's input. In the second chain, it takes the generated content and further transforms or expanded. And in the third chain, which is optional, will clean, refine, or format the final result of the user. Actually, we will use a parser for this. So each step has a single job, and together they create a smooth, controlled workflow. When we invoke the sequential chain, the LangChain automatically runs each segment in order, passing the output of the first chain into the second and then into the third, giving us a polished final result. So this will make your workflow significantly more organized compared to trying to squeeze everything into one huge prompt. And instead, we break the logic down to smaller, understandable units and let the chain connect them. That is the real power of a sequential chain, turning a complex operation into a predictable, well-structured pipeline. Now, let's move on to its implementation. We will first import our chat class. So that way is going to come from LangChain underscore grok import chat Then from .env, I'm going to import load underscore .env. From LangChain underscore core dot prompts, I'm going to import prompt template. From LangChain underscore core dot output parsers, I'm going to import structured output parser. Sorry, it is string output parser. Then I'll call the function load.env and then actually define my model. Now let me define prompt 1. So prompt 1 will use prompt template to define a template which will say generate detailed report on our topic. Since we have a placeholder, we need to define input variables here. Input variables, and then input variables will contain this topic. Then we'll have prompt 2. Prompt 2 is going to be about generating a summary of the content generated by prompt 1. So here what I'm going to do is generate a 3-point summary of the following text. And then I'll have a text placeholder, and similarly I need to have an input variable with text. Now I'm going to define my parser, which will be from string output parser, or str output parser or string output parser. Now I'm going to define my chain. So my chain will first use prompt 1, then the model, then prompt 2, then the model again, and then okay, so before we pass it on to prompt 2, we'll also use a parser, then prompt 2, model, and then finally a parser. So after this, I can invoke this chain easily using invoke function, and then I need to provide the starting context, which is the topic that is required in prompt 1. So the topic again is going to be aliens, and then I can print and see the result. Okay, so in this code we have multiple prompts where prompt 1 will be generated. It will pass to the model. The output will be parsed using str output parser. Then it will be passed to prompt 2, and then prompt 2 will be passed to the model, and then the output will be generated by str output parser, and then the final output from here will be seen in the terminal here. So let me clear this and then run the file. We will not be able to see the intermediate results generated by these tools here, but we'll only see the result after this particular parser. In order to visualize or see the result or the intermediate result of the chain, we need to introduce a monitoring tool, and we already have a tool in the LangChain ecosystem called LangSmith, but that will be for the further videos. Okay, so finally we have received a 3-point summary of our provided topic. So this is how we implement sequential chain in LangChain. Now we move on to conditional chains. In many real-world workflows, what we want the system to do next depends on the situation. Not every piece of information follows the same path. Not every input deserves the same treatment. And definitely, not every user message should trigger the same response. Imagine you're building a support system. Some users send praise, some send complaints. Some provide neutral feedback. Each type of message deserves its own specific meaningful reply. But if we try to handle all these cases with one fixed chain, the workflow becomes rigid and the output starts to feel generic and unnatural. That's because not all tasks are sequential and not all tasks are parallel. Sometimes the workflow needs to branch, to split paths and run different logic depending on the result of a choice. This is exactly where conditional chains shine. A conditional chain introduces intelligence in the workflow itself. Instead of following one straight line, the chain can evaluate something, make a choice, and choose the correct path to follow. It's like adding a brain to the pipeline. In the example we'll be doing, we're simulating something extremely practical, responding to customer feedback, but in a way that's tailored to the sentiment. Here's the workflow we're designing. First, we classify the sentiment of the feedback. Is it positive or is it negative? The system must choose. Then, based on that decision, take a different path. So if the sentiment is positive, we generate a friendly, appreciative reply. And if the sentiment is negative, we generate a thoughtful, empathetic response. And if something unexpected happens, we have a fallback message. So this is a perfect real-world example of conditional reasoning. One input, one choice, two completely different workflows. And the beauty of conditional chains is that all of this happens automatically. We don't manually check the sentiment. We don't manually choose the right path. The chain itself handles the branching logic behind the scenes. And this is what makes conditional chains so powerful. They let your AI pipeline adapt to the situation just like a real human workflow would. Now, let's move on to the implementation of this conditional chain. So first we'll import our chat grok, load.env, prompt template, str output parser, and then I'll also keep a pydantic output parser. Then I'll import runnable parallel, runnable branch, and runnable lambda. Then from pydantic, import base model and field. And then from typing, we import literal. Okay, so load the credential from .env file, define a model. Let's call it model 1. This is going to be a llama model. Now I'm also going to define a str output parser object. So for the feedback, let me define a class which will take in the base model from pydantic. And then inside this, I'll have one field, sentiment, which is going to be a literal. Basically, I'll have two options, positive and negative. And then if I need to explain this, I can use field. The sentiment of the feedback must be either positive or negative. Let me do word wrap so that you can see everything fit inside one screen. Now I will define parser 2 using pydantic output parser, and then the pydantic object is going to be feedback class that I've created. Now let's do prompt 1. It will be generated from prompt template. The template is classify the sentiment of the following text into positive or negative. So I will provide a feedback. This will be a part of my placeholder, and then I'll also provide my format instructions because I need the output to follow this pydantic output parser or the format that I've defined in this feedback class here. Then I'll define my input variable. Input variable is going to be feedback, and then I'll also define a partial variable. So this partial variable is going to be format instruction, and then this will come from parser2 dot get format instructions. Now let me create my classifier chain. So this will contain prompt 1, and it will contain model 1, or I might only have a model. Okay, I have model 1. Then it will contain parser 2. Now I'll have prompt 2, and this will do the following. So write an appropriate response to this positive feedback, and then I'll provide the feedback. Again, this is a placeholder, so I need to define my input variables as feedback. Similarly, I'll have prompt 3. I'll just copy prompt 2 because it is not going to be changed much, except I'll call this a negative feedback and then pass in the negative here. Now I need to create a branch chain. So my branch chain will be created using this runnable branch class. And inside this, if my sentiment is positive, then for that I'll define a lambda function. So x dot sentiment equals to positive. Then I want to run prompt 2, model 1, and then parser. Else, if the sentiment is negative, x colon x dot sentiment equals to negative, then I want to call prompt 3, model 1, and then parser. Okay, so this should have been prompt 3 here. So prompt 3, model 1, and parser. And for default, I'll call runnable lambda x, and then basically I'll return no valid sentiment found. Now finally I'm going to define my final chain. So this will contain my classify chain as well as my branch chain. Now let me invoke this final chain using the invoke function. And then what I need to provide is a feedback. And then maybe my feedback is going to say this is a beautiful place. Then let's see the result. And then let's see if this positive feedback will generate a positive response to it or not. So let me clear this and then run 3.conditional chains. Okay, it says no valid sentiment found. Let me elaborate this, which has a lot of amazing historical insights, and the people are also very good. Thank you for having us here. So let me check again if I've done anything wrong. So positive, negative. This should be sentiment of the feedback, and save it and then run it again. Still says no valid sentiment found. So let me check whether I've done anything wrong here or not. So this is sentiment. This is correct. It should be a literal with two options, positive and negative, where the sentiment of the feedback must be either positive or negative. This is also correct. Now I've created parser 2. Here I've passed in feedback and then the format instructions from parser 2, which is also correct. And then here I have called prompt 1 model 1 parser 2, which is also correct. Then I have prompt 2, which basically says to write an appropriate response to this positive feedback, and it is also good. And in prompt 3, write an appropriate response to this negative feedback, which is also good. Now if the response is positive, I want to invoke prompt 2, pass it to the model and parser. And then if the response is negative, then I want to invoke prompt 3 and pass it to the model. Let me not have this default value. because the model might get confused with this particular default value here. Or even if I remove this, let's see if we get an error. So if I run this again, okay, so runnable branch must default must be runnable. Okay, so I need to keep this, and then we'll say no valid sentiment found. Uh, let me change the temperature of my LM here. So let me keep it to 0.7 and then run this again. Okay, it still says no valid sentiment found. At least what it is doing is, or let's say the sentiment is neutral for this particular case, and then change our sentiment here. My stay here was horrible. You people are stupid. And then run this again. Okay, so it did identify the negative sentiment and then generated the the response for this particular negative feedback here. Okay, so this is how we implement conditional chains in LangChain here. Now we move to the final type of chain, which is the parallel chain. So sometimes when we build AI workflows, the problem isn't about choosing one path or the other. Sometimes the challenge is speed, efficiency, and the ability to get multiple things done at the same time. In many real world scenarios, a single input can be used to generate multiple outputs. For example, if you have a chapter of text, you might want notes for revision, a quiz for practice, a summary for quick reading, and a study guide for students, all based on the same source material. Now, if you were to run each of these one after another, first produces the notes, then wait, then generates the quiz, then wait, then makes the summary, then wait, you waste time, you waste compute, and your workflow becomes unnecessarily slow. But what if all these tasks could happen simultaneously? What if your pipeline could take the same text, split it into different branches, run each branch independently, and then bring all the results back together? And this is exactly what parallel chains enable. Parallel chain let your workflow perform multiple tasks at once using the same input. You're not doing sequential work. You're not branching based on a condition. You're simply letting the chain split into multiple workers, each focusing on a different goal and then combining the outputs afterward. It's the closest thing to multitasking inside an AI application. So, in the implementation, you'll see we take a single block of text, a piece of content, maybe about a certain topic, and we use it to produce two different output at the same time. First, a short, simple note, something clean and minimal, which is good for revision, and then a set of quiz and answers, something interactive and useful for learning. Both tasks will run in parallel, which means there is no waiting for one to finish before starting the other. And once both pieces are ready, we merge them into one polished comprehensive study response, a document that contains both the notes and the quiz. So this is the real power of parallel chains. They'll allow you to transform a single input into multiple meaningful output, all in one coordinated process. Whether you're making study materials, generating variations of content, or building multi-output AI tools, parallel chains will allow your workflow to scale horizontally, fast, neatly, and efficiently. So now let's go to the implementation of this parallel chain. So just like in the previous implementation, I'll first import ChatGrok class. And then from .env, I'm going to import load.env from LangChain core.prompts, import prompt template from LangChain core.output parsers, import str output parser, and from LangChain core dot runables. I'll import runnable parallel. Now load the credential in the beginning. Then I'm going to define two models here. So model 1 is going to come from ChatGrok. The model name will be Llama 3.3. I'll have another model, model 2, with the same LLM, but I'll use these in two different parallel workflows. So I'll have prompt 1 using chat prompt template. Sorry, it will be using prompt template, and then a template is going to be something like generate short and simple note from following topic. So I'll provide a topic here, and then since this is a placeholder, so I'll also define input variables, and inside this I'll provide a topic. I'll have prompt 2. Let me recorrect the spelling here. Prompt 1. I'll have prompt 2 that will say generate 5 short question answer from the following text. Template equals to, and then I'll provide a text placeholder here. So I'll also need to pass an input variable called text. And then I'll have prompt 3, which will say merge the provided notes and question answers into single document. So I'll provide notes and QA. And since both of these are our placeholders, I'll now define my input variables. Template equals to, okay. So input variables, I'll have both notes and QA. Okay, so I'll also define a parser using str output parser class. Now let me define my runnable chain. So my runnable chain will use runnable parallel to define this chain, and then I have two paths for this. For nodes, I'll pass prompt 1, model 1, and then parser. And for QA, I'll pass prompt 2, model 2, model 2, and then parser. Now let me also create a merge chain. So this merge chain will have prompt 3, model 1, and then parser. Now let me declare my final chain. So my final chain will be, at first we'll run a runnable chain and then a merge chain. Okay, so yeah. So maybe what I can do is I can provide a topic here, or directly invoke the model. Basically, let me invoke the model using my invoke function in the final chain. So final chain dot invoke. Okay, what do I need to pass? I need to pass the topic first. Okay. Okay. So let me do something. It's not going to be topic. It is going to be text here. So what I'll do is I will prepare a text from somewhere. Let me just paste this. So this text is about support vector machines. Let me remove this. So I'll paste this and then do a word wrap so that you can see what the text is. You can put any text that you want. So basically I have this text. Now finally I'm going to invoke my final chain dot invoke and then pass in the text here. So based on this text, I'll generate a note as well as Q&A and then merge these both into one. And finally, let me print out my result. So what happens here when I run this code is, let me run this first. So what happens when I run this code is, there are two parallel chains going on. First is for the nodes. The second is for the Q&A. Now these two chains will run parallelly, and then once both of these chains are complete, then it will be passed through this particular merge chain here, and then merge chain is going to generate a string result which contains, let me elaborate this. So this is going to contain a comprehensive note as well as the frequently asked questions, or basically the question and answer section here too. So this is how we implement parallel chain in LangChain. And that brings us to the end of this session. So we explored how chains give structure to our AI workflows, starting with simple chains, moving into multi-step sequential pipelines, branching logic with conditional chains, and finally parallel chains that let us execute multiple tasks at the same time. And by now, you should have a clear sense of how powerful and flexible LangChain becomes once you begin connecting these components together. So this is the foundation that allows us to build real production-grade AI systems that are modular, scalable, and capable of handling increasingly complex logic. But this is just the beginning. In the next videos, we're going to step into more advanced concepts in LangChain, deeper routing, agent architectures, memory, tool use, and everything you need to design intelligent autonomous AI systems. So if you enjoyed this breakdown, make sure to like, subscribe, and follow the entire LangChain Masterclass series, because things are only getting more interesting from here. Thanks for watching, and I'll see you in the next one.